Hello guys, welcome back to my channel. Today we're going to be exploring the total surface area of a triangular prism with the use of the GeoGebra software. So bear in mind that a prism has a uniform cross section. So if it's a triangular based prism, at any point that you cut the cross section, you're going to end up with a triangle. So the first thing I want to do here in GeoGebra is to create a triangle, and that's pretty much all I need to do in order to get my triangular based prism. So let's go right ahead. So I'm going to input 3 points. So let me put one here, one here, one there. And then we simply select the polygon that we want, and we're going to join this to get a triangle. Now that we have our triangle, I'm going to access my three-dimensional view. So here we go, 3D graphics. Okay, so we have the screen split in two. Now, because this prism cross-section will be a triangle, all I need to do with this flat surface in the three-dimensional view is just to stock a set of triangles above this, right? So technically speaking, when I click on this, I simply just need to give it a height because it's going to be triangles going all the way up. So let's say we have 4, right? So there we go. It's just like a projection of triangles. And of course, we have a uniform cross section over here. Now, let me change it. Let me give it a better color. Now, what I'm going to do is that I'm going to rotate this figure. There we go. You can see that the sides are rectangles if you look carefully. Right? So all the sides are really rectangle apart from the cross section, which is a triangle. So when I turn it down like that, there we go, we have a triangle. And if we turn it up there, we notice that the base is also a triangle. So we have triangles going right across the section. But all the other faces really are rectangles, as you can see. So we have 1 rectangle, 2 rectangle, 3 rectangles. And then we have 1 triangle at the top. We have a next triangle at the base. So technically speaking, here we have 5 faces. And bear in mind, we're talking about the total surface area. So we're talking about the area of all the faces. Now we're going right into exploring the net. Now what I've done is that I've made some adjustment to the colors. So when I show you the net, you can actually pinpoint each face. So let us go right ahead. So here we go. So this is the net of my figure. Now, here you can see the top triangle, which is in green. You can see the bottom triangle here, which is in yellow. You can see, and of course, you can match the associated faces. So technically, if I want the total surface area of this prism here on the right, it would be like I'm finding the total area of the net. So I would have to find the area of the top triangle, which is this one, the bottom triangle, the sides, which are all rectangles, and that is a critical concept here. So let me put the figure together so you can look at what happens. There we go. Look at the figure in closing. All right, so technically it's a triangular base prism. So as we said before, it's like a stockpile of triangles. But when we separate out the net, we can see that we have different faces. The two main faces are the faces of a cross section being a triangle, which is critical, but the other faces are actually rectangles. And there we go. There you see it. So we have 3 rectangular faces and the 2 triangular faces that forms the cross section of this prism. One of the critical things I want you to get from this is that you have to form a conceptual understanding of this figure, because in an exam scenario, you will not be able to adjust or to manipulate it to look at the net in such a simpler form. So understanding this conceptually from here will make it easier for you. And of course, there are a lot of places that we use triangular prism, because here you can notice that it actually forms a slope. And at home, you might have something that you use to catch the door. It's normally something that looks like this, a triangular prism. All right, so you can examine the figure, look at the faces, look at what happens, and then of course you can put this inside of your imagination. So you can picture or you can visualize the entire net when trying to work out this figure here. Very important. Alright guys, here's an example of a typical question that you could probably see on an exam paper. So it says, find the total surface area of the prism below. Now by looking at this prism, clearly we can see that this is a triangular base prism. As you can see that the cross section is actually a triangle, alright? So the cross section is actually what we refer to as the base at times. So we're not necessarily talking about the bottom of the thing when we talk about the base. We're talking about the uniform cross section. So in order to find the total surface area, I need to be able to find the area of all the faces, which means I need to be able to identify all the faces. From looking at GeoGebra previously, we know that the triangular base prism has two triangular faces, which is a cross section, and it has three rectangular faces. So this is what we're going to do. Because we can't see the face at the back, we can probably put in some broken lines to represent that. So I'm just going to put in some broken lines here. So in this case, we could probably we have A, B, C, D, E. We could probably put F around here. Good. Now, so my total surface area, which I'm going to shorten and call it TSA, would be the area of course, the two triangles. And we can always start with the uniform cross section because that is always easier to work with. So it would be the area of A, B, E, plus, and note that these two faces are actually the same area. So we can simplify the area of one multiplied by 2. But let's just lay out everything. Plus the area of CDF plus the area. Now let us look at the bottom face, which is ABCF. So we have area of ABCF. Of course, we have the back and we also have the front. So let us go with the front. So we have area of BCDE, and then finally the area of the back, which is AEDF. AEDF. All right. Now, of course, starting with the triangular faces, we know that the area of a triangle is half base times height, which is a perpendicular height here. So in this case, the base here, when I'm looking at the triangular face ABE, the base would be 8 and the perpendicular height as indicated in the diagram is actually 3. So it's going to be a half times 8 times 3. And of course, because the two triangular faces, which is AED or ABE and CDF, they're both the same because they are the uniform cross section. We can multiply all of this by 2. So we'd have counted for these two. All right, now let us look at the area of ABCF. ABCF. So we are looking at the bottom there. And the bottom there, of course, we know it's a rectangle. All right. And since it's a rectangle, we can say that AB is the width, and probably we can say that BC is the length. So here we're going to have plus 8 times 14. What about the area of BCDE? Now BCDE, of course, is that side there. But because the cross section there is actually an isosceles triangle, what it means is that that face, which is BCDE, and the back face, which is AEDF, is actually the same area. So once I find the area of one of them, I can simply multiply the area by 2. And this is only applicable because it's an isosceles triangle. If it were probably a scaling triangle, I would have to separate them and find the area individually. So the area of this face at the front here, since it's isosceles, it also means that this length here is 5 centimeters. So the width is 5 centimeters and the length is 14 centimeters. So I'm going to have 5 centimeters times 14 centimeters. And of course, we said that the back, which is AEDF, has the same area. So we can simply multiply all of this by 2. We're going to make use of our calculators, and we can even put all this inside our calculators. So this will give me 276 square centimeters. Now it is imperative that the unit is there, because without the unit, it is just a number. All right, so in order to work this out, the total surface area, we simply just need to break down the faces one by one. But of course, from GeoGebra, conceptually, we know what the faces are. Once we are able to identify the cross-section, which in this case is a triangle, we know that all the other faces on this figure are rectangle, and it is three-dimensional. So you can use your imagination based on how we examine the net in GeoGebra. Alright guys, we have a second example on screen. But as you can see here, this triangular prism is actually a right, so we can refer to it as a right triangular prism because the cross section is actually a right angled triangle. Now, we can insert some dotted lines to show the back and the bottom of this diagram here. So let me go right ahead and insert some dotted lines. So we could probably start with the area of the cross section, which is AED or ADE. But here's my problem. No. It's a right angle triangle, and we know that the formula is half base times height. However, we don't know what the height is, which means we're going to have to find the height. But look at the front of the figure, which is ABCD. That face there is rectangular, so we know that the opposite sides are equal. So what it means is that if BC is 5 centimeters, AD is also 5 centimeters, which means that to find AE, I could use Pythagoras theorem, because that would actually be the perpendicular height that I need. So let us go over here and apply that there. So we can say that AD squared is equal to AE squared plus ED squared. So I'm going to have 5 squared equal, and AE is what we want, so we have AE squared plus 3 squared. So we have 25 equal AE squared plus 9. And of course, we transpose this, so we carry over the 9. So I'm going to have 25 minus 9 equal AE squared. So 16 is equal to AE squared. So we square root both sides, which means that therefore AE is equal to 4 centimeters. So right here, the perpendicular height is actually 4 centimeters. So it means that we have everything we need now to go ahead and calculate the total surface area. So the total surface area would be equal to the area of AED. And of course, because we know that both sections of the cross section here, which both triangles are the same, we can say times 2. So this would account for both faces, AED and BFC. All right. We can also talk about the area of the front, which is the area of ABCD. All right. Let us look at the back, which is ABFE. So we have area of ABFE. And finally, we have the bottom, so we can say the area of, so probably we could say DCFE, DCFE. And we have all information. So this would be 2. The height here is 4 centimeters. And the base there is 3 centimeters. And of course, it's half base times height, right? So here, probably I need to put in the half. And of course, you can put in a centimeter, but for now, I'm going to leave it out. So I'm going to have a half times 4 times 3. So you can see the numbers clearly. What about ABCD? ABCD is the front. And of course, the width is 5 centimeters and the length is 12. So we have 5 times 12 for that. Plus the area of ABFE. And of course, ABFE is the back there, which is also a rectangle. And of course, if you look carefully here, if this is 12 centimeters, up here says also 12 centimeters, because the opposite sides of a rectangle are equal. So we can have the length there being 12 centimeters, and of course you can see the width there is 4. So we have 4 times 12 centimeters, plus the area of DCFE, which is the bottom, so DCFE, and there we have 3 centimeters by 12 centimeters. Of course, all this is just calculator work. You can simply put all this inside of your calculator. So this actually becomes 156 square centimeters, right? So all we have to do is analyze it, visualize each face, find the area of each face, and add up all the faces, and we have our result.